Okay. All right, welcome. You're all doing well. We have chapter 3 to start today, so we'll start chapter 3 today, continue on Monday. The exam over chapters 1 and 2 will be next Wednesday. So in preparation for that, you're welcome to access the study guide there. So the study guide is not an answer key, but it should be used as a guide to help on points of emphasis. So for today, just not too long ago, posted the chapter 3 PowerPoints. You can follow along there. So, welcome, Ty. Okay, so chapter 2 is on linear kinematics. So that's describing the motion of objects in terms of displacement, velocity, acceleration, including projectiles. And so now chapter 3 is on to kinetics, which is all about force. So how forces affect the motion of objects and bodies. So the topic of linear kinetics focuses a lot on the laws that were created in the late 1600s by Sir Isaac Newton. And so in his book that he wrote in 1686, titled Principia, he described these 3 laws that all revolve around how forces interact with bodies or objects. So, simply stated, each law is here. Every object persists in its state of rest or uniform motion in a straight line, so you can replace the word uniform with constant, unless it is compelled to change that state by forces impressed upon it. So in order for an object or body to change its state, there has to be an unbalanced force. So the net force has to be not equal to 0. If it is equal to 0, then there's no change. Second law, force is equal to the change in momentum per change in time. For a constant mass, force equals mass times acceleration. So you see there the mathematical expression of Newton's second law. The net force applied to a body or object is proportional to the acceleration for a constant amount of mass. So for a constant mass, the higher the net force, the greater the resulting acceleration. And then the third law, for every action, there's an equal and opposite reaction. So we talk a lot about that, especially in labs with the vertical ground reaction force that you calculated this week is a great example of that. And we showed an interaction with time. So the greater the amount of time it takes your body to come to a stop, the lower the impact force will be versus a shorter time period. So remember, question 3 was coming to a stop in 1/10 of a second. The resulting impact force and G's that your body feels much greater with a shorter period of time. So we'll talk about all of those things in this chapter. Okay, so let's take one law at a time. So for Newton's first law, if no net force acts on an object, so we can say that in that case, out of all the forces acting, there's no net force. So in other words, all the forces are in balance. The net force is equal to 0. That object will not move if it wasn't moving to begin with, or it will continue moving at a constant velocity in a straight line if it was already moving. So Newton's first law applies to objects that are both at rest, but also in a constant state of motion. So reverting back to chapter 2, if velocity is constant, what's acceleration equal to? Yeah, so if final velocity equals initial velocity, then acceleration equals 0, which is what Newton's first law is all about. All forces are in balance, so net force is equal to 0. So in terms of projectile motion, we talked about different components such as vertical and horizontal. So which component does gravity affect?
Vertical.
Yeah, vertical. And what's the rate of acceleration regardless of whether we are traveling up or traveling down? Yeah, that's right. Yeah. So that means that there's an acceleration. There's a constant acceleration or there's a constant change in velocity. An object will either be slowing down in the positive direction, or an object or body will be speeding up in the negative direction. So in other words, in terms of the vertical component, Newton's first law wouldn't apply because there's acceleration going on vertically. What about horizontally? If we ignore air resistance, how would you describe the horizontal component of projectile motion? Yeah, it's constant, which applies really well to Newton's first law because there's a constancy in the state of motion, so there's no change. There has to be an external force acting on an object before it will change its state of horizontal motion. So, of course, air resistance comes into play if you're outdoors. Indoors, horizontal motion would be constant. So other practical examples, trying to bring in some application here. So you've probably done wall sits, right? So that's a constant amount of tension. So constant tension type exercises. So various types of planks and so on. Bottoms up kettlebell carries. So you're applying a constant amount of force. So an object has no change in its state of motion. So we could equate this with isometric muscle actions would be a great example of Newton's first law, where the force from your muscles is equal to the reactive force from the ground, and everything stays in a constant state. So when weight equals reactive force, there's no change in the state of motion. So if any of you have done overhead barbell squats, very, very challenging, advanced exercise. And so the upward reactive force on the barbell applied through your hands is equal to the downward weight of the barbell acting into your hands. And so the weight stays in a constant position. So several different ways of interpreting Newton's first law. I've listed 4 of them here, but basically it all comes down to if the net force is equal to 0, an object will stay at rest, or if it was already moving, it will continue to move at a constant velocity. If an object is at rest or moving along at a constant velocity, the net force has to be equal to 0. So as soon as the net force is not equal to 0, then an object is going to start moving if it was at rest to begin with, or it will stop moving if it was moving along at a constant velocity, or it'll speed up. So Newton's first law also has some special application in terms of collisions. So objects or bodies that collide. Each object or body involved in a collision has a certain amount of momentum. So momentum is a word that you've probably heard a lot with application to sports. So with Newton's first law, we can talk about the conservation. In other words, the total momentum of a system of objects is the same before and following the collision. So no change in total momentum would apply to Newton's first law. So perhaps we need to define momentum to start with, and so momentum, at least linear momentum, capital L is the symbol, and then linear momentum is equal to mass multiplied by velocity. So objects or bodies that have a large mass and objects or bodies that can also move at a high velocity are going to have a lot of momentum. So when I think about that, I think about football athletes, American football athletes. You've got 300 plus pound athletes, very large in mass, that can also run really fast. So that sets up a scenario where you're going to get some pretty dangerous collisions, right? You've got two objects or bodies that are running towards each other. They both have a lot of mass and they both have a lot of velocity. So the collision is going to apply a lot of force to each of those bodies. So we can consider two objects in a collision together in a system. And so that simplifies the analysis if we consider both objects together as part of one system. We'll see what I mean in just a moment. So the total momentum of the system remains constant at the time point before and at the time point after the collision. So that makes things simple. So in practical terms, that doesn't always work, because in sports like American football, athletes wear pads. And pads are designed to do what? An athlete gets tackled. It's a lot better scenario than being tackled without pads, right? Like in rugby. Rugby is like American football without pads. So there's a little bit of deformation and loss of energy and impact force because of the addition of pads. But for right now, let's consider that 100% of the momentum is conserved from the time period before to after the collision. So we have two different types of collisions. We're going to assume at this point that momentum is 100% conserved with each of these. So we have elastic versus inelastic. Sometimes inelastic collisions are called plastic collisions. So in a perfectly elastic collision, okay, we're assuming total momentum is conserved at this point. So the objects or bodies will separate following the collision. So for example, if I was to take a basketball and drop it, and it's going to fall and bounce off the ground, if that basketball bounces to the same height that I dropped it, that's a perfectly elastic collision. But in reality, what happens? What really happens? I can drop a basketball from 6 feet. It's going to fall. It's going to hit the ground. Is it going to bounce to the exact same height that I dropped it from? No. So there's a little bit of loss in momentum from before versus after the collision, because the basketball is losing some of that energy as it impacts the ground. Okay. So, but at this point, we're assuming that the momentum is perfectly conserved. Perfectly inelastic collisions. Same thing, total momentum is still conserved, only now the objects or bodies stay together following the collision. So two different scenarios where we look at the total momentum before, and that is equal to the total momentum after, with the collision in the middle. We'll go over some examples. So most collisions in American football are relatively inelastic. So what that means is the objects or bodies tend to stay together, but there's a little bit of loss of momentum due to deformation of pads and so on, which is a good thing because those pads are designed to absorb impact. So the more impact that's absorbed, the greater the loss of momentum. But before we get to that, let's assume that we're in a perfectly inelastic or perfectly elastic scenario. Okay, so here's your practice problem number 1. So this is just study notes for you. Okay, so mathematically, before you read through this problem, I want you to look at the formula here. So we have 2 athletes, and the first athlete has a certain amount of momentum. Okay, so we'll call that the running back. So prior to the collision, the pre-collision velocity is abbreviated with a lowercase u. Okay, so the pre-collision velocity of one athlete, the pre-collision velocity of the second athlete, so they each have mass and velocity. And then after the collision, as you'll read here, they're moving together as one object. So 2 masses after the collision with 1 velocity. So v is the post-collision velocity of the combined masses. So an 80 kilogram running back, so we'll call that mass 1, collides in midair with a 120 kilogram linebacker, okay, so we'll call that mass 2, at the goal line during a goal line stand. Okay, so first question, is mass a vector? Is mass a vector? No, it's a scalar quantity, so we don't have to define direction, we just want to know the magnitude. So we have that. So goal line stand, we see this all the time on television. Just before the collision, the running back had a velocity of 6 meters per second. So the running back has a mass and the running back has a velocity. So they have a certain amount of momentum. The units for momentum are kilogram meters per second. Kilogram meters per second. So it makes sense because those are the quantities that you're multiplying together. Okay, so mass 2, 120 kilograms. Okay, so the running back had a velocity of 6 meters per second towards the goal line, and the linebacker had a velocity of 5 meters per second in the opposite direction. Okay, so question, is velocity a vector?
Yes.
Yeah. Let's call 6 meters per second positive. You will notice that the 5 meters per second is in the opposite direction, so that's got to be negative. So what you're going to do is calculate what the total momentum is prior to the collision. So you're going to multiply mass 1 and velocity 1, which is 6 meters per second, and add that to the product of mass 2 and velocity 2, which is negative 5 meters per second. So you're going to get a total momentum in kilogram meters per second. Let me know what you come up with when you have that. So 80 times 6, and then 120 times negative 5. And you add those collective momentums together, you come up with a total momentum. What'd you get?
Negative 120.
Yeah, negative 120 kilogram meters per second. Negative 120 kilogram meters per second. Okay, so let's keep reading here. So if the collision was perfectly inelastic, so not really, but for our case at this point, we'll say it is. Momentum is 100% conserved. Would the running back be moving forward and score a touchdown just after the collision, or would the defense prevail? So what you're looking to solve for is the post-collision velocity. So you would take mass 1 and mass 2, add them together, 80 plus 120. So you'd have a total mass of these athletes moving together after the collision of 200 kilograms. And then how would you solve for velocity then?
Divide by 200.
Yeah, so you divide that. And then what'd you get for the post-collision velocity?
Negative 0.6.
Negative 0.6. So did he score? No, because the velocity is a vector, there's a direction to it, so they're collectively moving in the opposite direction from the goal. So do you have any questions on that one? Any questions on that one? We okay to, did everyone get negative 0.6?
Could you explain that math part again?
Sure, yeah, so you'd add the masses here, so the running back and the linebacker would have a collective mass of 200 kilograms. And then we already calculated this part over here, and what did we say it was negative 120 kilogram meters per second. And then you just, to solve for the post-collision velocity, you divide by the combined mass to get negative 0.6. Because of that's negative, you can tell that the post-collision velocity is going away from the goal line. Okay. All right, so that brings us to the coefficient of restitution then. So what are some words you think of that are synonyms with restitution? Restitution. So what are some other things that could fit that description in this context, you think? Think of dropping a basketball. So I dropped a basketball from 6 feet, and gravity accelerates it towards the ground, and it impacts the ground, and then a certain amount of the momentum it had before it hit the ground is restored after the collision, as indicated by how high it bounces. So if it was perfect, it would bounce to the same height that I dropped it from, but there's some momentum that's lost in the collision with the ground. So restitution, or maybe recovery, how much recovery of momentum takes place after the collision relative to the momentum before the collision. So it's usually abbreviated with the letter E, so lowercase e. So there's no units, and it's on a scale from 0 to 1. So 1 is perfectly elastic. 100% of the momentum is conserved before to after. To 0, which is perfectly inelastic, still 100% of the momentum is conserved. So in reality, it's on a continuum where we do have some of the momentum and energy lost from before to after the collision. So usually you have somewhere between 0 and 1. So we'll give you some examples. Ball sports are nice. It's easy to conceptualize because the ground doesn't move, and the ground has a really high mass relative to anything that you're dropping onto it. So all we really need to know, if it's the ground that we're dropping something, the pre and post collision velocities of the ball to calculate the coefficient of restitution. So in other words, the coefficient of restitution describes the bounciness of the ball. Is that a relevant factor in sports? So the coefficient of restitution would relate to a certain air pressure, right? The PSI, the pounds per square inch that you're putting into a football or a soccer ball or a volleyball would directly determine the bounce height when dropped from a standard height. So there's actual rules on the coefficient of restitution for sports. And to make it easy, the coefficient of restitution usually equates to a certain PSI, which you can put that amount of pressure into a ball and it would be the correct coefficient of restitution. So the calculation here is E, which is the coefficient, is equal to square root of the bounce height divided by the drop height. So if we had a perfectly elastic collision and the bounce height was equal to the drop height, what would your coefficient of restitution be? What's the square root of 1? 1, right? So perfectly elastic with 100% conservation of momentum. So here's just a few still frames. Even the face of a golf driver, as well as the ball, deforms just a little bit during that impact. So a baseball bat with a ball, a tennis racket with a ball there, so how much tension is in those strings can affect the amount of energy that's restored as the ball comes off the racket. So you'll need to remember that equation, square root of bounce height divided by drop height. So here's some examples. So USGA, so United States Golf Association, driver is 0.83. That's pretty darn elastic, isn't it? So that's close to 1. So the total momentum that the club has before impacting the ball is almost completely transferred into the ball with very little loss of momentum. And I like to use the word energy consistent with momentum, and you'll see why I do that when we get to chapter 4. But energy and momentum really are kind of synonymous because an object or body that has more energy will have more momentum. The coefficient for a wooden bat is 0.55. So with a wooden bat, you're losing a lot of the momentum for the ball before and after that collision. What would it be for an aluminum bat? Higher or lower? Higher, which means what? Practical aspect. The ball is coming off of an aluminum bat much faster. What are the implications for maybe pitchers? Pitchers ever get hit? Yeah. Especially in cases of aluminum bats where there's not enough time for a pitcher to react and put their glove up. So wooden bat, there's less, the ball is coming off the bat with less velocity. So there's more loss of momentum. For a tennis ball on a rubberized court is 0.73. So let's see, we'll go back to this clip in just a moment. It's a football clip, so you'll like it. But let's do this next slide first. So NCAA men's basketball, a ball must bounce to a height between 49 and 54 inches when dropped from a height of 72 inches. So that's 6 feet, dropping height, hits the court, bouncing to a height between 49 and 54 inches. So if you would, can you calculate, say, the coefficient of restitution for if it's bouncing 54 inches? So remember, so bounce height divided by drop height, and then take the square root of that to get the coefficient of restitution. So 54 divided by 72, take the square root, 0.7, 0.8, somewhere in there, 0.82, so, yeah, okay. What, exactly? 0.87, okay. So, again, it's a lot easier to just put 7.5 to 8.5 pounds per square inch of air into the ball. For racquetball, must bounce to a height between 68 to 72 inches when dropped from a height of 100 inches. So if you want, try that one. So 72 divided by 100, take the square root, you get the coefficient of restitution. Excuse me. What did you come up with for that one? 0.85. Yeah, 0.85. So, okay. So before we get to this, let's go ahead and back up. So I promised you a video clip here, so we'll watch this. So this is about collisions in football.
When we watch football on television, it's difficult to get perspective on just how big and strong the players are. because they're all big and strong. So our question is, what would happen to a regular guy if he goes up against an NFL player? Could an average guy survive the lineup scrimmage? To gain some perspective, we hit the road and travel to the Sports Science Outdoor Testing Facility.
Okay, giant biomechanics.
And to help us conduct this test, we recruited a man who personifies the raw power and brute force of the NFL. All-pro defensive tackle, Chris Jenkins. Chris is one of the hardest hitters in the NFL. With textbook technique for exploding through an offensive lineman.
When I want to get under a man's pads, it has to do with my explosion. I'll start with my feet, and I'll roll up through my hips, and I'll put everything into my hands. And then when I explode, everything rolls up.
To execute this experiment, we need an average guy. So we scraped the middle of the barrel and came up with this guy, sports science host John Brinkus. Standing 5'8" and weighing 160 pounds, John is aggressively average.
He's written a really good book about all the experiences on this show.
Chris Jenkins, we've measured a lot of collisions in football. The one thing that we really don't get at home is the perspective. I mean, how big are you?
6'5", 360.
Okay, I'm 5'8", 160. So when was the last time you were my size?
7th grade, I think.
7th grade. So what we want to do is a one-of-a-kind experiment. We're going to have you, the NFL superstar, going up against me, the average Joe. We're going to go mano a mano, head-to-head, and measure that collision.
To measure the impact an average Joe would experience on an NFL lineup scrimmage, we're wiring up both test subjects with cutting-edge hardware.
Both Chris and I are going to be wearing an inform accelerometer around our waists, and this is going to measure the transfer of energy from him to me, which can't be good for me.
If he's gonna stand over there, I'm gonna toss him. And I'm gonna do it as hard as I can, and or as far as I can, and I'm gonna get as mad as I can. It's gonna be the real thing.
Wait, I can't even figure out how to get my arm through this. This is not good.
While our host struggles with the incredibly difficult task of putting on a jersey, Chris does some simple warm-up exercises.
That guy is a beast. He's pushing the two-man sled all by himself, just like it's nothing.
The average NFL defensive lineman weighs almost 300 pounds, and he battles offensive linemen who average about 320. So our 160-pound lab rat is clearly in way over his head.
You look like a kicker.
I hope all the average Joes out there appreciate this, because I'm about to get my bell rung.
Let's do this.
Time to find out how an average guy would try to stop an elite NFL defensive lineman.
Jesus. Look at that fast. You barely made it on the mat. Yeah.
You alright?
Ow, that hurt. Oh, that didn't feel good at all.
So to answer the question, what happens to a regular guy when he goes up against an NFL player? Well, he goes up. Data from the Inform accelerometer reveals that at the peak of his flight, John's head was almost 9 feet off the ground.
All of that power drives straight into John, producing this tremendous collision, transferring all of his energy across, literally throwing John out of the way.
So how much force did Chris use to launch John into orbit? Our cutting-edge motion capture technology reveals the answer. John's mistake is rising up too quickly, which raises his center of gravity, decreasing his stability. A smart lineman like Chris stays low and aligns the angles of his body for maximum impact. He does this by creating two 90-degree angles with his body's big levers, the arms and the legs. His shins are in line with his forearms, and they draw a straight line through the center of his target. By creating this straight line, his optimal foundation of leverage, Chris is able to launch John with 600 pounds of force. And worse, John returns to Earth with a painful 1,600 pounds of force. And if we extrapolate this data, the numbers are amazing. The average NFL game has over 100 plays, and in each play, about a dozen players collide at the line of scrimmage. The sum total of these collisions generates a staggering amount of energy, 32 million joules. That's over 7.5 million calories. Believe it or not, that's enough energy to launch a 160-pound projectile, like our lab rat, over 28 miles into the air.
But it was fun. I haven't had a chance to throw shot put since high school, and it felt good to be able to launch somebody.
And even after such a punishing hit, our lab rat was so committed to getting the science accurate that he took another hit. And another. And another.
Yeah.
So anyway, he's written the host there, John Brangus, has a good book where he talks about all of his experiences hosting that show. I think it ran for like 3 seasons with some pretty amazing experiments. Okay. All right, so we are on to the next practice problem. So a warm hockey puck has a coefficient of restitution of 0.5. So that's a lot more bouncy, right? Well, a frozen hockey puck has a coefficient of restitution of only 0.35. So in the NHL, the pucks to be used in games are kept frozen. So the coefficient of restitution should have a coefficient of restitution of 0.35. During a game, the referee retrieves a puck from a cooler to restart play, but is told by the equipment manager that several warm pucks were just put into the cooler. To check to make sure he has a game-ready puck, the referee drops the puck on its side from a height of 2 meters. How high should the puck bounce if it is a frozen puck? So that's the problem. So we want to write down what we know. If it's a frozen puck, what the coefficient of restitution is 0.35, right? And so that's going to equal the square root of the bounce height divided by the drop height. So the drop height in this case is 2 meters. So it's a little harder to explain the solution without opening this. So we write down what we know, right? 0.35 is the frozen puck coefficient of restitution, and that's going to be equal to our bounce height divided by our drop height. so we know the drop height is 2 meters, so we can rewrite this as 0.35 equals the square root. I'm just going to put BH for bounce height, and then we know this is 2.0 meters. Okay, so what we're solving for is the bounce height. So another way to rewrite that equation to solve for what you want is going to be, this is the same thing, taking 0.35 squared is equal to the bounce height divided by 2.0 meters, like that. So this over here is the same thing as this. So, and solving for bounce height BH is going to equal 0.35 squared times 2.0 meters. So the bounce heights, the answer is going to be in meters. What you get for your meters?
0.25.
Is that 0.25? Okay, good. 0.25, or that's about 10 inches. 10 inches on that. So do you have any question on that one? Okay, so everything making sense so far with all, okay. All right, so let's keep going. Okay, so now we're to Newton's second law. So Newton's second law is really just a special case of Newton's first law. So the difference is that now the net force is not equal to 0 anymore. So if the net force is not equal to 0, then you're going to have an acceleration. So with the first law, net force was 0, so acceleration was also 0. So Newton's second law is really just a special case of Newton's first law. So net force no longer equal to 0. Acceleration is proportional to the force impressed on a constant mass. So the greater the amount of force, the greater the change in the state of a body or object. So we can write this equation several ways. The first of this chapter, we said force is equal to mass times acceleration. We can also rearrange that equation to solve just for acceleration. So acceleration is proportional to the mass and proportional to the force and inversely proportional to the mass. So if mass is constant, greater acceleration is produced by a greater amount of force. So another example for baseball. So the force that the bat applies to the ball in that collision is dependent on the mass of the bat. Okay, so, and also the acceleration. So how fast can an athlete swing a bat? So bat speed is a significant performance factor for baseball. So a lot of athletes will have these little devices that they can put over the knob of a bat. Will give them real-time feedback on their cell phone app on how fast each swing was. So swing speed, just like golf is in baseball, is really important as well. Okay, so this is going to be a group activity. So you'll be working together. Okay, so you can work maybe in so perfect. So you guys, and then Bright and Tommy, and then just like that, okay? So this is on the importance of relative strength. Okay, so comparing Olympic weightlifting with powerlifting. So what are the two lifts that are contested in the sport of Olympic weightlifting? Yeah, snatch and clean and jerk. And so we take pieces or components of those two lifts or do variations of those lifts for maybe athletes in other sports, but the actual sport of Olympic weightlifting is the snatch and then the clean and jerk. So typically, the snatch is about 80% of what someone will be able to do for a clean and jerk. So powerlifting then, there's three lifts that are contested in that. Used to be 4, but now it's just 3.
Back squat.
Back squat,
Bench.
barbell bench press, yes. Barbell deadlift. And I'm not sure, I'll have to look up the history again, but it used to be overhead press was another measure for powerlifting as well. That one was taken out of the sport. So how do you compare two different athletes that have different weights? So you might say, okay, well, total up how much they lift and divide by their body weight. But that's not quite the best method. It's a simple method, but not quite the best method because the progression is not linear. And so you'll find that out as you read this article. There's 2 different ways of comparing athletes in the sport of Olympic weightlifting. It's the Sinclair coefficient. In the sport of powerlifting, it's the Wilks equation. So if you've done the 3 lifts that are part of powerlifting and you want to compare yourself to another lifter, you can use the Wilks equation. Same thing if you're an Olympic lifter and you want to compare yourself to another lifter of different body weight, you can use the Sinclair equation. So what would be the best way to work on this? So you can click here. This is the article. And so pound for pound lifting, who is stronger, Wilks versus Sinclair? And so you'll have 1, 2, 3, 4, 5. So you'll turn in one sheet with everybody's name on it, answering these 5 questions. And then as a practical example, what I'd like you to do is, what would the Sinclair score be for the following female weightlifters? So you're going to access this website. If I can get this cooperate here. So you'll access this Sinclair score. And so the Sinclair coefficient. So for each of those examples, it'll calculate it for you automatically. The documents are also included on how they get there, but I just want you to use the automatic calculator. So female, you'll put their body mass here in the second one in kilograms, and then you'll put their total right here for both the snatch and the clean and jerk together. So you put that all together, and then you calculate to come out with your Sinclair score for each of those Olympic weightlifters. And then for the Wilks score for powerlifters, so the first 2 female weightlifters, second 2 male powerlifters, you'll use the Wilks score. And so that's right here, so you can just put in the total. So we'll just go with pounds is fine for the Wilks one, their body weight and their total for the 3 lifts. So you can see right here, lifter A has a body weight of 190 pounds. Their squat is 455, bench press 295, deadlift 515. So you'll add those together, and that's what you'll put into that calculator. Same thing for lifter B, 165 pounds is their body weight. Squat 405, bench press 245, deadlift 455. So let's take about maybe like 10 minutes, work on that together, and so you'll turn that in for your participation points for today. So 2, 2, 2, 2, and 2.
Which formulas for relative strength? Yeah. Sinclair's weightlifting, and then Wilkes is power. Difficult to compare. I don't know. Oh, I only have a sketchy knowledge of mathematics. Me too. That's what I was to Sinclair. It's like seeing how it would be if they're bigger, but the other one is seeing how they'd be if they're larger.
So kind of an interesting read if you really want to compare yourself to another person.
So you actually want us to write down the normalization procedures?
No.
Or just the coefficient?
So, which question?
Three. Are the normalization procedures different?
So,
If we never put
the question that you're asking yourself in the Sinclair equation is what would I total at the super heavyweight level? So you're taking a lighter lifter and comparing them to a heavier lifter, and you're saying, okay, I'm a light lifter, what would I total if I was in the heavyweight category? And that allows you to compare a lighter lifter to a heavier lifter, because you're taking the lighter lifter and estimating what their total would be if they were a heavyweight. That's what the Sinclair does. The Wilk equation, it actually goes in the opposite direction. So if you're a heavy lifter and you want to compare with a lighter lifter, it's taking a heavy lifter and saying, okay, what would you total if you were in the 51 kilogram category?
Oh, so then that's
So
like the
your
standard.
Sinclair is estimating up, Wilkes is estimating down.
That's why you
That's
can't
the
really
key.
compare them between each other.
Right.
Because one's for heavy.
For three?
So is that what you want us to say?
It's like
Hmm.
the one
Yeah.
extra more correlated. It's like 80%. Small variances.
It's much more complicated than the show. Yeah, sometimes you go up. So you can,
So questions 4 and 5 are right at the end of these two paragraphs.
How is that not correlated?
This paragraph is interesting right here and really true if you think about it.
they don't go.
So do that.
And then you can also put
How about do that too?
There's scores in there, yeah.
So just don't correlate, period. So it's like Olympics is like decent.
So make sure on the calculators that you, online calculators that you enter the total.
Fairly decent, but not that great. It'll be like typical. One percent question.
Maybe if you know what your, some of your lifts are, you could maybe put your own numbers in there to get a total.
You clicked female, the weight, and her total weight, and that gives you this. There's 2, there's only 8.
Anybody know yet who's better, lifter A or lifter B? what was their Sinclair? You get like a
That's true, yeah.
327. What do you get for lifter B? Okay.
What?
Oh, yeah, I forgot we don't have to know how to do it.
Anybody know on the Wilk score yet? For the this one in
B.
pounds.
55 kilograms.
Make sure you total those carefully.
So we're doing a Sinclair score for both snatch and
No, you total them up. So you enter their total kilograms right here, and then their body mass here. So, let's see. So 55 kilograms, so 55, what's 93 plus 118 kilograms?
How about 211?
Okay. So I came out with 302. How many of you came out with 302 for the lifter A on the Olympic weightlifting?
Yeah, we should do that.
It's a female, isn't it?
Yeah, I got 327.
And click on the female.
Aren't you on the?
You're on, yeah.
No, that's female.
Did Lightning put it on?
Yeah.
I can go back. That would come out different, so it's,
Oh, I
So it's
thought.
I thought it was the other way around.
so 302.18 for lifter A. So let's see what lifter B. 74 kilos. So mass of 74 kilos. 112 plus 142. 354, right?
I'm scared. I feel heavy or light? I feel nothing. Some feet.
Everybody get 304.6.
Heavy.
The other one, so lifter B for the female Olympic weightlifters is the better lifter by 2 points, 2 Sinclair points.
It's 165 pounds.
So it's kind of neat to have like a standardization process where this is based on world championships, so the best athletes, and then anyone can take their scores and put them in, and you get your coefficient.
I'm trying to read the PowerPoint ahead,
So
I
the
can answer
two
questions right now.
males' body weight was,
Velocity. Oh, maybe the highlighted first use as to guess
first
the
guy
answers.
was 190
I know this one. So magnitude.
pounds.
Velocity, take the test.
What'd you get for the total on first guy here? 455 plus 295 plus 515.
1265.
1265. So there's 374.84.
Yup.
Yeah. How'd the other person do?
Worse, horrible.
65. What was their total?
1105.
357. Oh, no,
Okay, so it looks like lifter A. So both lifter A and lifter A were the best.
Should be, I think the first one for the girls we got B
B.
was the best.
Because of 302 and 304.
B, oh, okay. Yeah, 304 versus 302. Lifter B and lifter A. So kind of interesting, that's a good way to really compare with a group of people, rather than just dividing by body weight alone. Okay, so you'll turn in that one sheet at the end of today. Let's keep going here with second law. So, how many of you have ever seen one of these vintage bathroom scales? Okay, so one of my grandmothers is still alive. She's in her 90s, and she actually has one. and it's been there since I was little. So guess what I do whenever I go visit?
Step on.
I stand on it. Of course I do. Because I love the little dial and how it kind of back and forth and then finally settles in and love it. So, so that brings up another experience. So 30 years ago when I was an undergraduate at Utah State taking this class, my biomechanics teacher, Julianne Avendross Smith, brought one of these vintage bathroom scales, and one of our labs, we took it to the elevator in the building. And so, have you done that one?
We talked about it in
Yeah?
physics class last
Yeah,
semester.
so I don't know if I could find one somewhere and we have an elevator, I guess we could try it. Doesn't have much practical application though, but kind of teaches a point. So you're standing on the scale in the elevator and you haven't done anything yet, so the number on the scale is gonna equal what your body weight is, right? So then you push, okay, so you're on the first floor, then you're going up to the second floor. And so what you get is a reactive force from the elevator on the scale. So initially, the reactive force is greater than your weight, so you feel a little bit heavier initially when you're going from the first floor to the second floor, because the reactive force acting upward through the scale is greater than your body weight acting down. So there's an acceleration. So if reactive force is greater than your weight, then acceleration is going to be positive. So then, if we were to do this experiment between floors, okay, so the initial thrust upward, the number that you see on the scale goes up a little bit because there's an acceleration, so the number you see would be greater than your weight. And then it would kind of settle back in between floors. You would feel neither heavier nor lighter. So the reactive force from the elevator is equal to your weight. And then as you begin to decelerate to the top, your weight is greater than the upward reactive force. And so now you have negative acceleration and you tend to feel lighter as you approach the second floor. So the number you would see on your scale would actually be less than what your actual weight would be. So the scale would reflect the reactive force relative to your weight, is the idea. So just to reiterate here, initially starting up the upward thrust, you have a positive acceleration. The reactive force from the elevator is greater than your weight. Between floors, they're equal. And then approaching the second floor, you'd have deceleration, so negative acceleration, weight is greater than reactive force. So you feel a little bit lighter. So I was trying to think of a way to apply this, and I guess in some ways, as an example here, this would be a push jerk. And so you're generating a lot of force from your legs across your core and into the barbell. So initially, to get the bar moving, the reactive force from your hands into the bar has to be greater than the weight. Otherwise, the weight's not going to move. So you have positive acceleration to initiate the lift. And then towards the end of the lift, you'd have negative acceleration where weight is greater than the reactive forces as the lift comes to completion. Okay. All right. So talking about impulse and momentum. So oftentimes when we evaluate things, it's over longer time intervals. So it's not at an instant in time. So we need to consider that there's a difference between instantaneous acceleration versus average acceleration. More oftentimes, forces are acting over a longer time interval versus at an instant. So this equation of net force is equal to mass times acceleration this would be instantaneous acceleration. So at the instant we have a net force. Net force, you're comparing the reactive force versus weight. So the instant either reactive force or weight is different. Net force is no longer equal to 0. And if net force is no longer equal to 0, then you're going to have a change in the state of an object or body at that instant. So a change in the state of an object or body is a way of describing acceleration. Okay, now we also have average acceleration. So how do we calculate average acceleration? Remember, from what I'm going to do is just put net force right here for a moment. How did we calculate average acceleration? You remember? Chapter 2, not long ago. Okay, it was change in velocity divided by what?
Time.
Time. Okay. Average acceleration, VF minus VI divided by time. So if we multiply both sides of this equation by time, we have mass times velocity on one side of the equation. And from our earlier discussion today, what's mass times velocity? Mass times velocity is momentum, right? So really what you're talking about over here is a change in momentum. So mass stays constant, but if you have a constant mass that has a change in velocity, then you're going to have a change in momentum. Speed up or slow down, you're going to have a change in your momentum. So this is where we come into this concept. It's called the impulse momentum relationship. So what this says is that when a net force is applied over a time interval, you're going to have a change in momentum. And because mass is constant, okay, what that usually means is that you have a change in velocity that changes momentum. So a net force, which produces acceleration, and that net force is applied over an interval of time. It's not instantaneous. It's applied over a continued time interval. So an object or body is going to be changing its state. In other words, its momentum or velocity is changed over a period of time due to this net amount of force. So the greater the net force acting over a greater time interval means that this mass is going to have a greater change in momentum. So let's take a look at how this applies. So we can say, okay, so impulse is equal to force acting over a time interval. Okay, and so when you have a force acting on a given mass over an interval of time, there's going to be a change in velocity. So this is our complete equation. Impulse is equal to force multiplied by time, which changes the velocity of an object or body that has a constant amount of mass. So we have a couple different scenarios here. We have an impulse, in other words, a force applied over a period of time to increase momentum. Now when we say increase momentum, we mean increase velocity, because mass, the mass of your body, doesn't change during the course of a jump or a sprint. So what really changes is excuse me, is the velocity. So impulse to increase momentum. Okay, so Corey's not here today, but baseball pitcher. Okay, so the purpose of the windup is to do what? Why does a baseball pitcher take all that time and wind up and then throw a pitch? What's the purpose of taking this time? Yes, because if you take more time, you have this net force building all the way through your body. So the windup begins with what? The pitcher is pushing into the ground, right? It begins with the legs, and due to Newton's third law, action-reaction, right? Push into the ground pushes back, and we have this energy, this net force that is building over this period of time of the windup through all the segments of the body, the legs, the core, the arms, eventually culminating in release of the ball with the maximal amount of velocity. Does the mass of the ball change during the course of the windup? No. So what we're really talking about is applying a net force over the time period of the windup to impart the greatest possible velocity on the ball upon release. So lots of sports skills are the same way. You have a preparation phase. Sometimes the preparation phase is also called the wind-up phase, where you're building force through the kinetic chain over a period of time to maximize velocity upon release or upon contact. So lots of sports skills work like that. Now, the objective there is to increase momentum, but how about, do we ever apply, this will get into your lab 3 next week on the force plate when we talk about drop landings on the force plate, but applying forces over periods of time to bring a given mass to a stop. Yeah, we do that all the time, right? So this is positive acceleration going from 0 velocity to maximal velocity upon release. But what about the reverse, where we're starting with a certain amount of velocity and the goal is to bring the object or body to a stop by the end? Yeah, so don't we do different skills where the object is to bring ourselves safely to a stop? And a lot of times after we bring our body to a stop, what do? And so we go back and forth. We decrease momentum, bringing our bodies to a stop, and then immediately we increase momentum as maybe we change our direction. Now we're running in a different direction. So we have the coupling of these two things going on all the time, right? So what type of muscle action involves slowing something down? In other words, decreasing momentum. Lengthening muscle actions, deceleration. What type of muscle action? Eccentric. Eccentric actions, where we bring everything to a stop, are immediately followed if you understand the stretch shorten cycle, right? This is the stretch, and then after we bring everything to a stop, we reverse it and we get a more powerful action, right? Because we've stored all of that elasticity that we're then utilizing during the subsequent concentric action. So these two are connected together. We exert force over a period of time to bring our bodies to a stop, and an instant later, we're initiating force over a period of time to maximize velocity in a different direction, right? So how many in elementary school ever played egg toss with a raw egg? How many have ever done that? If you haven't done it, it's worth trying, okay? So you go to the family reunion and, you play egg toss, right? For whatever reason, okay? We've done it. Okay, so you're tossing an egg. How do you catch an egg without the egg breaking?
Soft. You brace.
Your elbows locked and your hands flat, right? Just as the eggshell's gonna break, right? So how would that apply here? How much time does that egg have to absorb impact if you're gonna catch it like this? None. So there's a relationship between time and impact. So the longer the time period, over which your body or an egg absorbs that force, the lower the average force, because you're taking more time to absorb that impact, which lowers the average impact force. So how does that apply with, say, our bodies? Yeah. So it takes practice to decelerate in the proper period of time to where our bodies can tolerate the impact. So with conditioning, do we learn to tolerate greater impact force? Yeah. And that improves performance because we can slam on the brakes quicker and then change direction without getting hurt. So a novice athlete, they may require more time to slam on the brakes to bring their body mass to a stop safely versus a more advanced athlete that can slam on the brakes quicker, can handle more of that impact force to bring their body to a stop and then quickly change direction. So does everybody understand the idea with impulse and momentum and how that works? So this is really the more relevant factor because more often forces are applied over time. Okay, so I believe that's it for today. So thank you. So let me get your sheet so I remember to put your points in. You just have a name.
Sorry, I'm all over the place. So, I'm confused. Okay, so, are all of the prisons gonna get into this, or only some? All of them?
I'll be right there.
Okay.
You have to know how to use them.
Yeah, I just earlier said no to questions, so I didn't know if we had